Okay, but I didn't want that. So it's not still part of my course. It will be. But I talked to a friend who's writing computer software, and he just shared, I didn't have it, he just shared the new software with me this morning. And I mean, it's old stuff in principle. But, so this is the Mandelbrot set, which probably you've seen a million times. But I want to show you some connections of what we are going. So who of you has not zoomed through this many times? You've all done and seen this?
I have seen videos of in YouTube where they are zooming in the video, but I didn't zoom myself. So does it count?
Half. You get 50 out of 100. And the others, but as I said, but you should do it yourself and really find what's interesting and where. So when you're somewhere in, somebody should tell you where you should be able to find out where you are, not just in the video. You shouldn't get lost in it, but find your own way. And there is this great video on 3 Blue 1 Brown. Has somebody checked that?
I think I have. You mean this reference?
Sergei Shemyakov, Aix-Marseille University. You should. We talked about homework, so we should check homework just after this.
What's the timeline? What's the time step?
And what's the grading scheme? Yes, I know that. In principle, so far it's just basic, and you can zoom in here. And of course, what you probably heard many times, that there are little Mandelbrot sets all over the place. And I want to tell you, not today, but one of the topics, why you find all those little Mandelbrot sets. I mean, this is here a bit, and then you can zoom in.
So this one is sort of binary. We have black and yellow.
Well, there is some color scheme. If you do it black and white, you will usually not see the black. So there's some coloring when it does escape, but how long does it take to escape? So here, I think, except for the center, most points numerically will escape because it's very thin in between. And the thin part you don't really see with black and white. And therefore, the coloring tells you something must be there.
On those red bins, there is also black white, right? For example.
So we can zoom in someplace, for instance, here.
So there will be black white. Okay.
Not only will there be black points, so one of the open questions is the Mandelbrot. This is part of the Mandelbrot set. Is it path connected? Work in progress. We discussed that. But whenever there is a transition between inside and outside, in every open set that intersects this, there will be infinitely many little Mandelbrot sets. And I tried to prove to you roughly why this is so, and what theory there is behind it. Or actually, if you see these things, that means the number of iterations, it's not good enough. And then you change the iterations to a bit more, and then you see it's better.
In what sense are there little Mandelbrot sets? Are those, so these are homeomorphic copies?
Homeomorphic copies.
But not affine copies?
Certainly not. That you can prove. They're not affine, but they're almost differentiable in a precise sense. It looks affine, and again, the question is, and that's an open question, it will remain open for a while, how much can they be distorted compared to actual little affine copies?
There are not a single one affine copy.
There is no single affine copy. In fact, none of, and well, here's a proof, so let me.
So in some sense, when you zoom in, you can just by looking at the picture, locate where you are in the region.
Right, in principle. Some people can do it in practice better than others, but in principle that is possible. And that's an art in its own right. So let me again. So I proved for you almost, homework to you, that this circle here is an actual circle of radius 1/4. Has anyone actually done this?
By the way, about those circles, those areas of period n, I don't understand why there is a number of them, which it is. I've read about which number it is. I don't know if I should say it, because maybe it should be a surprise for others. So,
Then we talk over pizza.
okay. But,
Secret pizza talk.
but I've calculated how many points that have at which the period there is an exact cycle of n, and it's not the same as a number of these n's. So there's no one-to-one correspondence between areas.
Oh, there is.
Is it?
There is. We have to get to it. Yeah, we'll discuss it. Anyway, you can prove that this thing here is the only perfect circle in the Mandelbrot set. And that comes out of algebra, Galois theory. And therefore, for all the little Mandelbrot sets, you don't have perfect circles at the corresponding place. So it's not an affine copy. Is that a convincing proof, roughly speaking? Anyway, so this is one thing I want to show you. Then I should.
When you say that it is the only perfect circle, you mean if there is, what is the more precise statement? Like if we find some disk in the Mandelbrot set, then.
So all these components, which are called hyperbolic components of various periods, these are all topological circles. But the only one which is a geometric circle has period 2. And that is algebra. And there comes another conjecture which somebody has to prove, so we can get into many of these things. If you're algebraically inclined, you have to compute some Galois groups. I computed Galois groups in my PhD thesis. But there's still some, this happened to be. So let me. This is the Mandelbrot set with some funny decorations. And this one has the advantage, if I click here on some little zoom, ignore the decorations for now. You see, for instance, this little Mandelbrot. No, this is maybe it's easier. Can I go back? Previous view. Previous view. So I can click, on this guy, on the parameter, then it's all new. I haven't played with it too much yet. So when I click on this parameter, I see the Julia set here on the second window. And if I click on a different parameter, I get a different Julia set. You see that? But so maybe.
Instead of having 0 as a starting point, we have this point as a starting point.
No, we have always 0 as the starting point. Well, for the Mandelbrot, it's always 0. But here, for the dynamical plane, we have z squared plus c. Now we start the dynamics with all points z in the complex plane. And we take a fixed parameter c for the polynomial. And I pick 2 that happen to be. And actually, you see, this is a period 3 component. So there is you don't see it, but there is a period 3 cycle in here. So that this disk goes to the second one, goes to the third, comes back after 3 steps. And this guy happens to be period 5, and you see this is going in 5 steps around this point. Just remember these 2 pictures. And now we do something different, completely different. I open the Mandelbrot. Do you remember this picture? That reminds us what this was. Right, so this is the space, and in particular, the black parameters are the bad cubic polynomials.
And this is cubic polynomial, and we already translated it to the simplest form with one parameter.
Right. So now we zoom into a little Mandelbrot set here. And again, whenever the colors change, every open set has a little Mandelbrot set. So now I go into this Mandelbrot set, and I do the same thing. I click on the parameter of here corresponding to, remember the previous picture, and now I get Newton's method here. And if I zoom in here, does this remind you of something? And if I click on this guy, they are homeomorphic. So you find the little Julia set somewhere when trying to, this is the plane of finding roots of cubic polynomials. And again, somehow it's all the same.
I mean, finding roots of cubic polynomials is just a map, rational map of degree.
Same as the polynomial. Degree 3 if it's a cubic polynomial.
Because it's 2 plus 1 on top and 3 on bottom.
P over P prime. It's the same. It's usually the same degree. It's a completely different map, and so in a way it's a miracle. But that's a preview, which I want to discuss some other time. I just wanted to advertise the connection. Today I want to discuss, without computer, something different. Yeah, right.
How do we get the set in the middle? Could you repeat
the black set?
Yeah, so like among these two pictures, the picture in the middle.
That's from the Mandelbrot set.
And so like we chose a value on the Mandelbrot set and
at the corresponding point in the Mandelbrot set.
yes, so then how is the this coloring
Well, just say it's black and non-black. The other colors are funny.
I think he's asking about, so in the Mandelbrot set, we take all the C's such that the series is bounded. Yeah. But here we take this starting point, we fix it, C, and we look at all the Z.
okay, so here we vary the starting point.
There's the parameter space, which is the Mandelbrot set in this Mandelbrane here. And on the right-hand side, there's the dynamics, when you fix a particular map and do the iteration of this map. Yeah, sorry, and thank you for helping. Maybe one more little thing here. I'm back here, this is the Mandelbrot set. And I zoom, no, I have to click on navigate. I zoom in to get a little Mandelbrot set here. You see that, friend? And here I click again on the corresponding parameter, which is here. Maybe I want to, you see this? And now get a Julia set, which looks funny, but when I zoom inside, it's the same picture. Or if I click, there was the other one here, I get that same picture. I should increase the number of iterations. Not this one, maybe it's one of those. The user interface is not very fine yet. Okay. They're a bit we'll get to it. I just wanted to advertise the software, which I got this morning, and I spent all the time playing with it. But I haven't practiced enough. Anyway, that much for this. Today I have a very different topic to discuss with you. But that will come, and I want to explain why you get the little Mandelbrot sets all over the place, and why this is a natural thing that is not a coincidence, and how it's connected to the rest of the world. Okay, can I stop this for now? So turn that one is off. Have we started the recording or?
Yes.
It's all okay. So then this is.
That's all recorded.
Okay, so greetings to the rest of the world then. That was a preview to what's coming next week. So like every good TV show, you have to say, please come back next time. And there's a little advertisement. The a bit annoying part is the board here is the narrow part. So today I want to advertise hyperbolic geometry. Have you heard of hyperbolic geometry? Yes, a little bit, or let's see. So I'm sure I can say something newer. So it is, let's first see what is the non-hyperbolic geometry. Do whatever pleases you. So we have, very good. We have simply connected back to complex analysis, connected subsets of the Riemann sphere. The first kind is the Riemann sphere itself. Can you see the Riemann sphere here? A round sphere, and it has spherical geometry, as you see. Second case is the complex plane itself, which is the same thing as the Riemann sphere minus a single point, for instance, minus the point infinity. And has Euclidean geometry. In the plane. I don't think I have to explain much to you. So, all the other simply connected, all other cases, let me call it U. And on the first session, we saw that it's always biholomorphic to the disk. That's what the Riemann mapping theorem says. So therefore, for the simply connected subsets of the sphere, in one case we have the spherical geometry, in one case we have the Euclidean geometry, and in all the other cases, if we have a geometry on the disk, this will be hyperbolic geometry.
When you say geometry, what do you mean by that?
You'll see it. Yes, I'm getting there. But this is kind of where it will come up. And that will make, whenever you have hyperbolic geometry, dynamics will be simple. Or put differently, all the interesting dynamics happens when there is no hyperbolic geometry. So let me, one example is H2, which is perhaps the simplest. The disk is obviously the same as the upper half plane. It's one example. And there is a map, which way around does it go? Here, the map phi. Phi of z is z minus I over z plus I. So this thingy, if z is in the upper half plane, then z is closer to I than, you have the distance to I and the distance to minus I. So if you're in the upper half plane, then this is less than 1 in absolute value. So you go to the disk. And if you're in the lower half plane, it's outside of the disk. So this is the map that sends the upper half plane to the disk. Or it's one of the maps. So, that's the upper half plane. And let me draw the upper half plane. And I want to define hyperbolic geometry. I want to define the distance, the hyperbolic distance between any 2 points. So here are 2 points, P and Q. And then I have some curve, maybe rho of t. And then the length of some curve rho is defined to be integral from 0, well, rho is from whatever, 0 t. It's a curve like this. I'm a bit cheap on notation. The Euclidean length is something like you break it up into pieces, and ds is the Euclidean length. And now I divide that piece, that thing by imaginary part of y, or more precisely integral gamma prime of t, or rho prime of t. This is the length of a tangent vector, divided by imaginary part of rho of t dt. That's a clumsy formula. Let me say what I really do. I break up, as I said, the curve into little pieces.
Sorry, in your definition, like xy are real and imaginary part, but then so we take imaginary part, maybe just y. Like I mean.
And y is positive, so we're in the upper half plane.
In the first integral.
Oh yeah, it's just y. You're right. You're right. As always, yes. Or maybe I should write dz here, and then s is. A simpler way is the length ds, the hyperbolic length, is defined of a little piece, is the Euclidean length divided by the imaginary part. Okay. I'm happy to have more guests, but you have to tell me your names. Again.
You asked us to repeat our names?
Yes.
Ivan and Petro.
Okay. Unfortunately, that's recorded also. Yeah. But so we just started defining the hyperbolic geometry. We did something else which was different, which you can watch on the video. But I defined the hyperbolic geometry on the plane. Simply, we have a curve, cut it into small pieces. It's the upper half plane in the complex plane. Every little piece has the Euclidean length the way you know it, and divide it by the imaginary part of where you are. So, this is a reasonably short piece. This is much longer. This has the same length in this, and this is much shorter.
How far we are from this?
Exactly. So you can view, if you like physics, you can have, this is a glass and you have, or liquid, you have different index of refraction. You're much faster up here and very slow down there. And by the way, everything that I'm describing here works in n dimensions, 2 or more. Three-dimensional hyperbolic space is the upper half space, and it's the distance to the boundary. And if you want to do it dimension 17, it's the very same thing. Okay? So that is the length of a curve. And then the distance, the hyperbolic distance between 2 points is, and that shouldn't be surprising, it's the infimum of the length of overall rho, length of rho, so that rho connects P and Q. The distance is the length of the shortest curve. Okay. And this distance is invariant by translations, that shouldn't be a surprise. Z goes to Z plus A, where A is real. If we have a horizontal translation, then the hyperbolic distance does not change. And it's also invariant by scalings. Z maps to lambda Z. Lambda is a positive real number. If I scale everything, then by say a factor of 3, then all the Euclidean lengths become greater by a factor of 3. But the imaginary part also increases by a factor of 3. And so all these things are unchanged. Okay. So, somewhere was it the Erlangen program by Felix Klein who said that geometries should always be described by the isometries that keep the geometry the same. And that's what we are doing here. And then there is one more invariant, and that's inversion. Z maps to, I want to say 1 over Z. But maybe I should say minus 1 over Z in order to stay in the upper half plane. So if this is radius 1, so at that point Z is here, then the inverse is a negative angle in 1 over.
Not minus 1, but conjugate of
Z bar, I think it's the same thing. It's not the same thing, but both is true. And yeah, by some, you can say flips, when x, y goes to minus x, y. And then you can compose this. The reason why I prefer inversion, this is holomorphic, while complex conjugation is not holomorphic. So that's, oh, and then there are rotations. They're a bit harder to describe. I can rotate, you pick any point, wish there was some red here, pick any point here, and then you view the upper half plane as a disk, hyperbolic disk. You see all the boundary points are at infinite distance. So it's a disk, you can rotate it. Let me visualize this much better. It is true that that way it's not so easy to see. Can I write here? I wish. So we delete this. And we assume, or we know the disk and the upper half plane are the same thing. So, oh, by the way, if I take,
maybe we can draw like lines that go to all the directions, straight lines from this point, and then it will be like easier to visualize this rotation.
Whatever straight lines mean. Yes, we can, but let's start something different. We are on the disk, which is, we have a biholomorphic map here, which I wrote down explicitly. And so this biholomorphic map phi, I can take the distance between any 2 points. Any 2 points map into 2 points here with the connecting curve. And I say the distance between these 2 points is, we can compute it here. And then we can, even this formula here, we can land here. And so this is the decisive formula for infinitesimal lengths. If we know that, then we can do the rest. So here there is a similar formula ds in the disk is dz 1 minus absolute value z squared. It's a little exercise to compute that these metrics are the same. So these are two standard models. There are many models for hyperbolic geometry. That is one and this is one. And here you see rotation is very obviously a symmetry. You fix this point, the whole definition is rotation invariant. So that's, sometimes this model is easier, sometimes this model is easier. But you see that here you have a rotation symmetry, and of course the circles become circles here also. Not concentric circles. These are the rotation images of circles when you rotate there. And you have radial lines which are like so. Yes, so one theorem is that isometries, any two points are connected by a unique shortest curve. And in this picture, it's always, well, let me just draw it fresh, perpendiculars, like so. Circles, well, there's an extreme case, vertical lines. And other than this, it is circles of this type. Yes, 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 yes. These guys are asking very good questions. Check out. You can play with this. I mean, this is a long discussion, and it deserves much more time than I can invest at this moment.
So they generate all fractional linear.
One more case of an exact. So here's a theorem. The isometries of H2 are the same as the complex automorphisms of H2. That's what you're saying. I may have translated it a little bit. But so the Möbius transformations, this is the form that maps to factor z minus a over something like this. And no, az plus b over cz plus d, and then ad minus, all of them real, ad minus bc, something like this. These are the Möbius transformations that happen to preserve the upper half plane. If you haven't seen any of this, accept it a bit like science fiction. One day it will become true. But you're welcome to ask questions anyway.
I saw this from Marina Gazowska summer school.
Number theory. What a nice connection. And of course, being connected to, when Marina presents this, yes, then must be true. Yes. What an honor to be compared here. Yes. Very much so. Yes. So, these are Möbius transformations. Az plus b over cz plus d. If you make a, b, c, d real with this condition, then these are Möbius transformations that keep the upper half plane invariant and the lower half plane invariant. So you get an automorphism of the upper half plane. And conversely, all the automorphisms are of this form. You want to ask a question? Well, I'm asking the youngest person. You asked them over pizza. But there are no miracles here. So, and yes, you can check all the, if you want to find all the automorphisms that fix a particular point. You can make that point the center here, then it's rotations. But you can also do something here. You take an inversion, then you're down there. Inversion at this circle down there. Maybe then you do a scaling, then you're here, and then you translate back. So this is a combination of what you had, and it fixes the same point, so it must be a rotation. So as you said, you can get the rotations out of these things, but maybe it's a bit more geometric. Okay? So, so geodesics, as I said, are these circles. Let me use a new color and draw in it and kind of prove why this is the case. You take any 2 points, P and Q, and we claim that the geodesic is the unique, there is a unique semicircle across them that's perpendicular to the boundary. And that is the shortest curve between them, unique shortest curve. Why is that so? Let's look at a special case. The 2 points are vertically, P and Q, above each other. Then we compute the length by taking any curve like so and connecting them. But whenever I have such a curve, I can project it horizontal to the vertical line. And any little line segment like so will get shorter. Because the height, the imaginary part is the same, but it becomes vertical and therefore more direct. You see that? Therefore, in this special case, whichever smooth curve I take, it gets shorter by the vertical line. So, therefore, if the 2 points are vertically above each other, then there is a unique geodesic which is part of the vertical line. Okay? Now what do we do? Translations preserve vertical lines. Scalings preserve vertical lines. All the others are generated by a single thing, the inversion. So the only thing you have to know is that if you have a vertical line someplace under inversion, it becomes a circle. And that I guess you've seen someplace. Have you? Then this is a nice thing to know. Or elementary. I'm always scared when something beeps, but if it's fine. You relax me, very good. Thank you for calming me down, yes. Okay, so I tried to calm you down mathematically. So this is, some inversion at the circle is a nice trick in elementary calculus, well, it's beautiful. And then, again, I'm not sure I want to go into it. But in complex analysis, you teach it also, that every Möbius transformation sends circles or lines to circles or lines.
It's not obvious, but it's classical.
If you look at it the right way, it becomes obvious. Plus, I mean, it's not so difficult to compute if you take a vertical line, take the inversion formula. Yeah.
I'm not sure what is the right way.
I don't want to spend time on it. So there are various ways. Maybe different people have different preferred ways of doing it. But in the end, it's one of the basic tools that one should play with. So, but that way I've shown that the geodesics always have this form. And the same, since this is the Möbius transform, geodesics here have the same form like so, or perhaps radii. Okay? So, And the same thing works so far for any dimension. Let me make a quick excursion. I want to do some dynamics today, but specifically in 3 dimensions. Actually, in any AN, the boundary is homeomorphic to the sphere of 1 dimension less. The boundary in a natural way. I mean, the boundary is always at infinity, but in this model it's obvious. Well, you have to, I mean, it seems obvious, but it's part of, you want to make sure you're not using the structure of the embedding, but an intrinsic property. And here the boundary is Rn minus 1 union the point at infinity, which again is a sphere. Specifically, for H3, the boundary of H3 is not just some 2-sphere, but in fact, it is our old friend, the Riemann sphere. What does this mean? You check the automorphisms of H3, which are translations or scalings or inversions. And they naturally extend to automorphisms of the Riemann sphere. So the Riemann sphere is the boundary, or you can view it, this is the complex plane union the point at infinity. H3, here's the room. Riemann sphere, we're standing on the complex plane, and H3 is the thing above. Right? And so then the isometries are translations of H3, which reduce to translations of the complex, or extend to the boundary, translations of H3. Same with scalings. And same with inversion. In H3 becomes inversion on the complex plane union infinity. So all the automorphisms of H3 naturally are automorphisms of the Riemann sphere. So you have something similar, that the isometries of H3 is just the Möbius group, or the orientation preserving symmetries, which is the automorphism of the Riemann sphere. Very nice connection. In the seminar on Wednesday, you're all invited. This is the basic. Here you get hyperbolic geometry in 3 dimensions, which is a huge world in its own right. And that's connected to what we're discussing today.
So there is a theorem that says that the set of invariants is enough to define the geometry, right?
This is Felix Klein's Erlangen program. I'm not sure whether it's a theorem or a philosophy, but it's a very meaningful statement.
Okay, then is this automorphism between the boundary of H3 and Riemann sphere an isomorphic?
No, certainly. Well, what is the boundary? It's a natural identification. So how do you... Is it an isomer? No, I would just say it is. The question is, how do you define the boundary? You want to define it without referring to the embedding of H3 into something.
Well, we can like look at geodesics that...
Yeah, you're doing the right thing. And then you really... So what I'd rather... So H3 natural... Every Hn naturally has a boundary. An intrinsically defined boundary. And with that respect, all the automorphisms of H3 become automorphisms of the boundary. And in the case of dimension 3, it becomes automorphisms of the Riemann sphere.
In H3, we have 3 coordinates, and the last of them is greater than 0.
Yes.
So like this boundary is like just a plane.
So here we have Hn. So then x is in Rn minus 1. when y is positive.
So on this intrinsic boundary, can we like extend the metric or no?
Not a priori, because the boundary is at infinity. So
this automorphism is just, so when we say automorphism of boundary, it's like just topological automorphism? Or like
well, no, in the boundary a priori is a topological automorphism. But in dimension 3 specifically, the boundary is a Riemann sphere. And then it's a holomorphic automorphism of the Riemann sphere. That may be a coincidence, but it's a profound coincidence. And therefore, in order to study three-dimensional manifolds, now I'm getting a three-manifold is the quotient of H3 by a discrete group. And this discrete group acts on the boundary. So in order to understand three-dimensional manifolds, you want to understand discrete subgroups of automorphisms for the Riemann sphere, which is a holomorphic dynamical system, like iteration of rational maps. So somehow it's very closely connected. And there's a big direction in something else. I wish, well, maybe I get to this on Wednesday or over pizza. It's just a little excursion that, have you heard of the Poincaré conjecture? So that's coming on Wednesday. The big three-dimensional manifolds is a huge topic. Most of the three-dimensional manifolds have hyperbolic geometry. And then you discuss automorphisms. You can discuss holomorphic dynamical systems on the Riemann sphere. So this is very lofty. And if you didn't get the details, come and talk some more, or just like science fiction, wait until it comes to you. Is this roughly meaningful?
What is this topic in math called? What is the name for all this theory?
Mathematics. Interesting. I like math when it's connected. So it's a bridge. On the one hand, the famous theory of hyperbolic three-manifold. And on the other hand, you have holomorphic dynamics, which can be both iteration of rational maps, or it can be these subgroups on the Riemann sphere. And this connection is called the Sullivan dictionary. Dennis Sullivan has observed that there is this deep connection, and a lot of mathematics. There has been progress on three manifolds, and there has been progress on rational maps. And every time somebody has proved a theorem on one thing, this dictionary has given at least ideas for proving something important on the other side. But that is kind of an advanced preview. I was planning to talk something much more elementary today.
With our questions today.
No, I enjoy that. Yes, Anderson, you are, and that's good. It would be boring otherwise. But I just want to make sure that not half the people get lost by the questions of the other half. So ask questions again. Yes?
Why is it reason to have infinity in high-dimensional sphere, like S3 unit is infinity?
No, in high dimensional, the boundary of Hn is R. Well, if you wish, you start by saying this is Rn minus 1 union a single point, which we call infinity. Okay? So some questions can be answered quickly. So, exciting topics, we can get back to it. But I want to, have more questions? Let's do something much more elementary. Dynamical systems, when they're hyperbolic, are, you can say easy, nice to understand, beautiful, or you can say boring, which is the same thing. And that's something I would like to discuss today, as much as I have time for, because this is a lot of explanation for a lot of dynamics. Well, we are starting to run out of time, which is a good moment to sorry, folks, yes. I mean, some people are very well organized and know exactly at the beginning of class, at minute 27, I will do exactly this. No questions, please, because this is then I'm a minute late. Plus, we have time from the computer connectivity issues. So, but I have to erase some things. Here is a beautiful, useful, and easy theorem. If U and V are, let me say, subsets of the Riemann sphere, they're both not the whole Riemann sphere and not the complex plane and simply connected. In other words, they're Riemann domains. Right? Every simply connected subset of the Riemann sphere, it's not those two, is a Riemann domain. So all of them have hyperbolic metrics. Okay? And F from U to V is any holomorphic map, complex differentiable on the whole thing. Then F contracts the hyperbolic matrix of U and V. In the sense, for all P and Q in U, the hyperbolic distance in the image of F of P, F of Q is usually smaller but could be the same, the distance in U between P and Q.
Isn't the matrix, the hyperbolic matrix on U and V like dependent on the holomorphism we choose with the disk?
Ah. These guys ask good questions. But maybe somebody can give good answers.
That's like this theorem also proved that.
So I think we have a unique map if we choose what point will be the center, and all other maps will be isometries.
So we have phi and we have psi. So what does then phi and psi define a priori different hyperbolic matrix here? So then, if you compose them in which order, you first take an inverse and then take the other. That's a map from the disk to itself, which is biholomorphic. Okay? And it's a biholomorphic map, it's a complex automorphism. And is it still there, or have I just erased it? The complex automorphisms of the disks are exactly the hyperbolic isometries. It's a wonderful question and a wonderful answer, right? Otherwise, the whole theory wouldn't make sense. Okay, statement is clear? So I have any U and any V, and both are Riemann domains, right? Biholomorphic to the Riemann, to the unit disk. And I have any holomorphic map F. You take any points P and Q, and then of course have image points, F of P and F of Q. And the hyperbolic distance in V is shorter or perhaps equal than the hyperbolic distance between the original points in U. Things always get shorter. Okay? And the fact that's equal is an exception. Usually it's really shorter. Exactly. And when you have contraction, then the dynamics cannot do much. So I want to at least sketch a proof for this using one of the profound results in complex analysis called the Schwarz lemma. Who of you has heard of the Schwarz lemma? 1, 2, 3, 4. That's the grading scheme. The further in front they are, you see that. Okay, so.
We are not sure like there is the same Schwarz lemma.
Is it about reflection?
No, it's not Schwarz reflection.
From the one about not from this to this?
Yes. So, the Schwarz lemma. A colleague of mine keeps saying if he has to go to a remote island for the rest of his life, and he can take only 3 theorems along, the Schwarz lemma would be one of them. Schwarz. Johnny. Oh, what's it? Black, like you. Yeah. I think that's the majority color here of the people. Okay, so if F is a map from the disk to itself, then holomorphic, of course. Every map should be holomorphic. Then either F of Z is strictly less than Z for all Z which are different from the origin, or F of Z is a rotation. So the second, you have a disk map from the disk to itself. Of course, the rotation keeps all distances to the origin fixed. And as soon as there is a single point for which the distance to the origin is not fixed, then everybody gets closer to the origin. Have you seen that? I will not prove, it's not a hard proof, but somehow I might lose myself. But the proof idea is simple. You define a map H of Z is F of Z divided by Z. And that's a holomorphic map that sends the disk to, you have to check it, it's a holomorphic, it's a map on the disk, and you have to check at the origin you don't have a pole. Because there's a 0 upstairs, F of 0 is 0. And there's a 0 downstairs, you can check that at the origin there's not a pole. And then you have to check that in fact the image is bounded by less than 1. So that means H of Z is less than 1. And then F of Z is Z times H of Z. Then we're almost there. Of course, you have to explain, especially why the values are less than 1, and this has to do with the maximum principle of holomorphic maps. It's easy to check. I think you find it in the appendix of my book. But I'd rather use this thing than go into it. But you should not you should think this is very useful, but you should not think this is miraculous or difficult. So with this, let's prove that little thingy here. This is the map F from U to V. I can send U, it's the Riemann domain, to the disk so that phi of P equals 0, and then we have phi of Q is somebody else. And here we have, again, a Riemann map again to the disk, so that f of p goes to 0, and here we have c of f of q somewhere else. Okay. This is by holomorphic by construction. This is by holomorphic by construction. This is holomorphic because we assume that's so. So the map that we get here, G, which is first phi, then F, then C, is holomorphic. Right? And it sends the origin to P, F of P, the origin. So we can apply Schwarz's lemma to this map. And now there are two possibilities. Either it's a rotation, and then all distances are preserved, or every point comes closer to the origin. In particular, this image point gets closer to the origin. But the hyperbolic distance, of course, the closer you are on the disk to the origin, but you see the hyperbolic distance there. Okay? Are you convinced? Yeah.
Yes, but it's too miraculous. So it's too surprising of a result to be convinced by the proof. I think. I understand the proof, but
where is the miracle?
Miracle is that holomorphic map of two such regions is a very powerful restriction on F.
It's the Riemann mapping theorem. And that's the theorem I would take on the island. Yeah.
It comes from the fact that, like, just being holomorphic is a pretty strong restriction.
And pretty natural. Yeah, but this is, so one of the reasons for the beauty of holomorphic dynamics is you have very powerful results, which at the same time are very natural. So if we can get back to, I don't know, the solar stability of the solar system, you see that dynamical systems is a big field, and a very difficult field, in applied mathematics in many directions. In holomorphic dynamics, we have the tools to make things precise. And yet, we get meaningful results that make sense even much more generally. So that's, I would say that's the beauty. That's the point of it. Okay, so what do we get out of this? If you have, now we haven't done any iteration so far. It's all been geometry. Iteration. So we have any Riemann domain U, and then we have a holomorphic map from U to itself. Then there may be exceptional cases when it's really an isometry. But except for these very special cases, it's always contraction. And in particular, the typical situation is that you have a fixed point. So then all we assume we have a Riemann domain, we have a map F from the Riemann domain to itself, which has a fixed point. Then everybody will converge to that fixed point. Which is, I think, a remarkably strong and surprising result. So that's what I'm saying. Dynamics is when you have a hyperbolic setting. It's very easy to the way of almost boring.
We can check in this proof that if either everything contracts or everything is isometric.
The only other case is if you have a fixed point, then it is really biholomorphic to a rotation like so. And then you get rotations in the same way. That happens, it's called the Siegel disk. After Carl Ludwig Siegel, a number theorist. Why number theorist? And why has Carl Ludwig Siegel, a number theorist, written a book with Jürgen Moser, a physicist, about celestial mechanics? There must be reasons for it. If we have time, we can get to, not today, but So there are these connections between number theory and celestial mechanics and everything. So that is a powerful theory, theorem for dynamical systems. And now I think we should mentally get ready for the pizza. So let me conclude with something in holomorphic dynamics. No.
So like either we get a fixed point in its isometry or everything.
So what are the possible, if I have a holomorphic map from a simply connected domain with itself. So what are the cases? Either there is a fixed point inside, such that everybody converges to this fixed point under iteration. Or, special case, there is a fixed point and its rotation, necessary by an irrational angle, Siegel disk. Or, if that doesn't happen, so if there is no fixed point, then there is a unique boundary point and everybody wants to go to that boundary point, which I haven't proven. That's a little more work. Not much, but... So that is the only three possible cases if you have a Riemann domain in a holomorphic self-map. So it's a powerful theorem, right? And now let me show you by examples that this helps you to understand dynamics of polynomials or of rational maps. So what can I erase? I have a nice picture, I have a nice lemma, and I have a nice theorem. Huh? But if you make the choice, all the people who watch the video later have to follow our choice. So think carefully.
There is a good place in the middle.
But then Schwarz lemma is less than theorem. But if, okay, yes. Somebody helped us make a decision. So now let's say f from C to C is a polynomial and always degree at least 2, otherwise it's boring. Okay, so then P of Z equals AZ to the D plus something like this. So if Z is large, then this is the nth iterate. We'll go to infinity. If n is large, then this term dominates, and it will keep dominating ever more, so we go to infinity. Okay? So I index P, so that, question?
I think I know what
You want to come and do it?
I can say it with the verb.
Okay.
So we can remove the large part that will converge to infinity, and then we will be left with a domain which is the Riemann
domain.
Riemann domain, and then we know what the dynamic will be.
Just about. It's not quite so easy, but in principle, that's exactly the spirit. So these are the I for infinity. They converge to infinity. And it's obviously, this is the neighborhood of infinity. So near infinity, that's what happens. And then we have Kp, we used that last time or the time before. That is the set of points that do not escape. It's called the Phil-Julia set. You can take pictures, but perhaps when it's full.
Yeah, so
Okay. Okay. So the basin affinity is open. If somebody escapes, then a neighbor of points will also escape. So the Phil-Julia set is compact. And it's not empty. There are always fixed points and periodic points. But now it may or may not have interior.
Why should it be clear that IB is open?
So there is a radius, and once you're outside, you go strictly greater. So there's a radius that if Z is greater than R, then P of Z is greater than Z. So if some point, if you're outside of R, then you go to infinity. And if you ever come to outside, then you do this with a neighborhood. If some point Z, well, the property is called continuity. So you take, if you have a point which is bigger than this, then there is a disk which still has a radius bigger than that. Now you have your point Z, and after 17 iterations you're here. Then the pre-image of an open set is open here, and that's the neighborhood of Z. Make sense?
Yes.
Okay, but I appreciate questions, and then some of them can be answered more easily. And this was one of them. Okay, now for the Phil-Julia sets, there are various possibilities. For the map Z squared, the Phil-Julia set is just a closed disk. The boundary is interesting. We have a fixed point at the origin, and indeed, everybody goes here. Then there's something let squared minus 2. The Phil-Julia set is the interval from -2 to 2. There's no interior. On the interval, it's invariant, something interesting happens. And everybody outside will go to infinity. There's something like Z squared plus I, and then the Phil-Julia set is called a dendrite. And again, this theorem doesn't apply. But there are other beautiful theorems. But of course, there are many other cases that we have seen. For instance, the famous rabbit, which we looked at before. And here we have a disk which goes, if you have a bounded, if the Phil-Julia set has interior, then every interior component must map to some other interior component, which maps to some other interior component, and let it come back. So then the third iterate finds the Riemann domain, which it sends to itself. Remember, we had such kinds of pictures on the computer. I don't have to show them again. And now on this domain, I can show you 3 pictures, 3 cases, and most of the time, there's a fixed, so let me show exactly when. Mandelbrot said, this is the period 3 component. You find those things. When you're in the interior, anywhere in the interior of this component, the parameter C from here, then you will have an attracting fixed point. You have a fixed point, 3 cycle, and everybody after the third iterate will converge to this fixed point under the third iterate. If you're on the boundary, a rational dense collection of boundary points, dense countable, rational points in fact, then it will converge to a boundary fixed point. And then there are some irrational boundary points in which you can have Siegel disks or not. And exactly when this happens was the fields matter for your course. So, let me just add one more. The Julia set is the boundary of the field Julia set. That's the interesting boundary curve. The Julia set. And Fp is the complement in the Riemann set of the Julia set, the Fatou set. And the Fatou set is always hyperbolic. So in the Fatou set, all this always applies, which makes the dynamics simple, and there are only a handful of cases. And maybe I should come to an end by saying, whenever you have a rational map and you have a Fatou component, it will maybe pre-periodic, but after some iterations, it will always become periodic. And that is a deep theorem proved by Dennis Sullivan. Heard the name Dennis Sullivan before? Abel Prize, laureate and such. And he proved it because he knew something about hyperbolic three manifolds. He had some techniques and methods on three manifolds that proved big results in three manifolds. And you realize there is a connection to rational maps and their dynamics. And as a result, he applied this, and he proved the Sullivan no-wandering domains theorem, which really means for rational maps, every Fatou component is periodic or pre-periodic. So that was an open conjecture by Fatou for 70 or 80 years. And then somebody working on hyperbolic three manifolds discovered the connections, and then it became nice and beautiful.
When was it proven?
Late 80s, I would say. Maybe mid 80s. No, early 80s. Let me change this. So in the early 80s, holomorphic dynamics started again. And there were 2 or 3 main reasons. One of them was John Hubbard, my PhD advisor, teaching the course on Newton's method and discovering, oh, we can discover something. That was 81 or so, or 80. And pretty much at the same time, Dennis Sullivan discovered his no-wandering domains theorem and introduced quasi-conformal mappings. And these probably were the 2 beginnings. Well, and then you could say Bill Thurston, when he was a postdoc at John Milner, and convinced Milner he should work on those. That happened roughly at the same time in the early 80s. And yeah, so that was. And Hubbard is still alive, Sullivan is still alive, Milner is still alive. Milner sent me birthday congratulations just a few weeks ago. So that was very nice and very pleasant.
Sorry to interrupt you, but we have to be
To go to the pizza.
right about now.
Well, that's the official announcement.
But the reservation is at 6:30, so...
Yes, and the pizza will be ready at 7. But we should, yeah. Okay, well, this is a strong argument. If there's still a quick question, I'm happy to answer it, especially from the young people. Could you roughly make sense of it? Well, yeah, you have to get used to it. I mean, I remember how many years it took me to get used to this.
So Julia set is only the boundary?
The Julia set is the boundary. And that's where the interesting things happen. On the Fatou set, which is the complement, you always have contraction, or almost always. So that's where it's simple is. And on the Julia set, you have chaos. I haven't defined chaos, and I don't like the word, but that's where the interesting things happen.
Is it always chaos?
Depending on how you define chaos, yes. And if you want to understand homework for you, take the circle z maps to z squared. We know inside goes to 0, and the outside goes to infinity. But what happens on the circle? Very simple question. And if you understand that, then all the other things can be understood easily.
There is some periodic behavior.
There is some periodic behavior. But for every period, the number of periodic points is finite. So of all the points, only countably many are periodic. And the interesting ones are the other.
So it's just a shift of 1-0 sequences.
Yes, yes, yes. Can there be a point, for instance, so that under this map, the orbit is dense on the circle? Dense. Well, if, by the time you made this, but... Okay, so this is where the chaos starts. Okay, so I'm supposed to say thank you for your attention.